Okay, questions? No questions? So everybody's got 100% on the homework problems? Josh?
For E, is an E2 reaction with the Cl, the ring with the Cl more stable, or an SN1 followed by SN1 with the Carbo anion?
Okay, so for problem E, we've got a tertiary halide being reacted with an alkynyl anion, and so the alkynyl anion. This is kind of a new. This is very much a new kind of nucleophile / base because it could do either one. In the past, what we've said is that when we're going to do E2 reactions, we're either going to use NH2- or the tertiary butoxide, and that's all they do is E2. But now we have something that can do both. So what we've said is that if it's this alkynyl anion plus a primary or a secondary halide, you're going to get what mechanism? We're going to get SN2, right? Now, the question about, well, what happens with the tertiary? Because this is such a strong nucleophile and base, there's going to be, it's either going to try and attack or it's going to deprotonate. So the time that it's going to take, for instance, to have the chloride leave and form a carbocation, it's already going to do something. It's either going to substitute or it's going to do elimination. So when we react one of these types of both nucleophiles and bases that's strong, we're going to say that is definitely an E2 mechanism. So it's not going to be SN1, E1, it's going to be E2. But this is the first of the bases that we've had, the base nucleophiles that we've had. We'll have other ones, such as alkoxides, next week, within the next couple weeks. But these guys always do E2, and so these can do either one, but we're going to limit them to either SN2 or E2. So that means that if it's an E2 reaction, how do I approach it? What's the first thing I should do? Get the alpha and the beta carbons. Identify the beta hydrogens then. And these hydrogens. So identify the alpha and beta carbons and then the beta hydrogens. Then make sure that the beta hydrogens can be anti-periplanar to the leaving group. Now in this case, I didn't give a stereochemistry with Bowler-dashed wedges, so it doesn't matter because these two hydrogens on both sides of the ring, either one of them can be removed. And with the CH3, since it's got free rotation, any of those hydrogens could be removed. But remember, those are the steps we take. You got to determine alpha carbon, then beta hydrogens. Which ones can I remove that are anti-periplanar? And then we look at the base. So we look at this base and we say, well, is it sterically hindered or is it small? If it's sterically hindered, it goes after the hydrogen that is most Small bases go after the hydrogens that are most... Okay. Small bases go after the hydrogens that are least sterically hindered. So most would be accessible. Because I want to form the product that is most stable, substituted. Those two go together. So in this case, your base is going to come in, grab that hydrogen, that pair of electrons is going to move to form the double bond, and the chlorine is going to get kicked out. And it doesn't matter whether you were to deprotonate the beta hydrogens on the bottom or on the top, you get the same product. So we're going to limit our choices here to SN1, to SN2 and E2. Any other questions?
Can you do like some examples of assigning oxidation states?
Sure. So in chapter 14, it's review up to the oxidation states, which it says is a review of chapter 12. And so in chapter 14, if you go through its review of like Markovnikov, anti-Markovnikov, I think Zaitsev, double bond, when you form a product of Zaitsev versus the Hoffman being the less substituted double bond. It's got stereoselective, regioselective, stereospecific stabilities of carbocations. And then it also has oxidation numbers of carbon. So we need to know the oxidation number of a carbon in order to determine whether it's undergone oxidation or reduction. So let's say I've got a CH3OH going to an aldehyde. So I've got methyl alcohol going to what's called formaldehyde. And I wanted to know, is that an oxidation or a reduction reaction? Anybody have a guess? What?
I think reduction.
Reduction? Anybody have another guess? Oxidation? Well, we really shouldn't be guessing. And the reason why is because if you remember, we talked about the basics of oxidation reduction, at least in lab last year, or last semester. Oxidation is when a molecule gains an oxygen or loses hydrogens, and reduction is when it gains hydrogens or loses oxygen. So that would make this one an oxidation. So this is an oxidation reaction. Now, remembering those rules, right? Oxidation equals gain oxygen loss hydrogen. Reduction equals loss of oxygen gain of hydrogen. That kept us from determining the oxidation number of carbon. Because then we have to go with the Leo the Lion says GER, lose electrons oxidation, gain electrons reduction. Or oil rig, whatever that stands for. Because I don't, like I said, I prefer the Leo the Lion better. So how do we figure out the oxidation number of carbon? They have 3 rules in the book, 3 steps. I I bypass that and just kind of remember a process as opposed to memorizing 3 steps. And here's what the process is based on. You're going to look at the atoms that each carbon is attached to, and you're going to decide which one of those 2 atoms is more electronegative or less electronegative. And when you look at the carbon-atom bond, if the atom is more electronegative than carbon, carbon loses the electron completely to that atom. Now, that's not what really happens. But in our bookkeeping, that's what we're going to do. If that atom is less electronegative than carbon, then carbon's going to take that electron from that atom. And if it's another carbon atom, they're tied. So there's no loss or gain of electrons. So for instance, methane. What's the oxidation state of carbon in methane? Well, is hydrogen more or less electronegative than carbon? Less. And so that means that for each one of these CH bonds, the carbon's going to pick up 1 electron. And when something gets an electron, 1 becomes negative. So that means that of the 4 bonds, the oxidation state on that carbon is going to be -4. Because that's the way we do oxidation states in organic molecules. It's all or nothing. You either take the electron from the atom, you give your electron to the atom, or you're tied and it's a wash. So for methane, oxidation is 4-. For this carbon, we'll give you 30 seconds. Do we all have an answer? So I can spin the wheel?
Shannon Atwell.
I got -3.
Do we agree? -3? Okay. I think that's right. So we got -1 from each of the hydrogens, right? And then we basically lose 1 to the oxygen, so there's a +1. Again, carbon losing electrons, that's loss, that's plus. Those 2 cancel. Uh-oh. No. Is it -2? So we've got 3 -1s and 1 +1. So that's -2. It takes a little bit of the negative and positive signs take a little bit of time to get completely used to. Let's look at that. So for the aldehyde, what is it? Everybody have an answer? What is it? Dylan, you had your hand up. 0? Do we agree with that? Kevin, did you agree with that? Anybody have another answer? That's a good question. That's a good question. Let's see. Where's my book? Okay, assign -1 to carbon bonded to each hydrogen or anything less than electronegative than carbon. +1 to bonded to each nitrogen, oxygen, or anything more electronegative. Assign oxygen to a carbon bonded to each carbon. You can artificially treat each sigma bond as an ionic bond. I don't see anything about double bond. So I think we treat the double bond as if it was one bond. Let's see. Oh, here's a good example. So carbon here. So carbon and carbon dioxide, if it's going to be +1 here and +1 here, it should be +2. What are they doing with all these?
It's like attached to 4 oxygen kind of. So
It does, doesn't it?
So it has.
So I guess I'll take that back. Maybe we should do the double bond each.
Yeah, like
1, 2, 3, 4. Yep. So we'd have to take the double bond into account. So did that change the first one? No. Good question. That's where we find the answer. You'll have to decide whether I knew that ahead of time or whether I'm just showing you where we find the answer. Okay, so in a double bond or triple bond, that's going to be 2. That's going to be +1 because the oxygen's losing. 2 +1s, a -1 and a -1, so a 0. So we're going to take each bond individually. I guess when they wrote that and they said sigma bond, they really weren't talking about you take each bond. So the question then is, as this carbon over here goes from -2 to 0, it's doing what? It's losing electrons, and so it itself is being oxidized. So we already said this is an oxidation reaction. It better be an oxidation reaction as it goes this way. And so in order to do this, I would have to put 2 electrons into methanol in order to make formaldehyde. So that's how we would do it. So if we said something like here we have, this is called a Cito Nitrile. Acetonitrile is a solvent. It's actually a non-hydroxylic, or it's an aprotic solvent that we could use for SN2 reactions. So what would be the oxidation numbers of its carbons? I'll give you a moment. We got answers? How about the one on the left? -3? Do we agree with that? That this one's -3, and then what about the carbon? +3? Do we agree with that? With these ones, you have to say plus. And then what would the nitrogen be? It'd be what?
Would that be it needs 3, and then it has 3 in the end, so 0.
We're just counting I think we're just counting how many it gets, right? I think it would be -3. These oxidation numbers, okay, so then you'd say, but hold on. Wait, I'm confused. Because they didn't add up to 0. But what am I forgetting? Now it adds up to 0. Because each of the carbons has lost an electron to carbon. So +1, +1, +1, +3, +3, -3, -3. Now it all adds up to 0. We could probably have come up here and figured that out too. So in other words, lone pairs don't play a role.
Can you explain where this might be like +1 instead of -1?
Because in the CH bond, they are less electronegative, so the carbon gets that entire electron. So what made this carbon -3 was getting 1 electron from each of the hydrogens. From the hydrogen end, it just lost it, and when you lose an electron, you become positive. So each one of those is +1, and hydrogen will always be +1 when it's attached to, unless it's attached to something that's less electronegative than it.
So why in the other ones is it -1?
Oh, the -1 that I wrote was for I was tallying up what was going to the carbons. That's what I was tallying up the -1. This is a -1. That's a -1. That's a -1. So the carbon ended up -2. This one, each one of those hydrogens ends up +1, including this one. So if we went through and we added everything up, the oxygen actually would be what? It would be -2. It would be -2 because it's getting 1 from the carbon, 1 from the hydrogen. The carbon's -2, so that's -4, and then 1, 2, 3, 4 +4, so it adds up to 0.
Is this different than the oxidation states we use for resonance and like to find out which one's the best resonance structure?
Yes,
Oh.
because those were formal charges. There's a difference. So this is not formal charge. Formal charge for this carbon would be 0. Because that rule is how many electrons does the carbon own and how many did it come with. That's the formal charge. Oxidation number is I'm just giving away its electron. So that's where it becomes confusing, and that's why I don't normally do oxidation number at the same time I do formal charge, because then it gets really confusing. In this case, that bond, either the electron goes to one atom or the other, and if the two atoms are the same, it's a tie. So the reason they're using the oxidation number is simply because they're trying to figure out, is the reaction an oxidation or reduction? What we do is we simplify it to simply say that's oxidation and that's reduction. So then we don't have to go through this. But you'll probably have to go through this on a couple problems that are in the chapter. So that's why we need to go over it. It's not standard procedure. Okay. that kind of make sense? I'm not going to give you any homework problems due for Wednesday because you've got the review sheet. But after that, I may draw up a new problem set, well, I will, that deals with reactions of alkynes, as well as what your homework problems are, and I may put a couple of these on there for extra practice. Any other questions? Let's see, yesterday we started probably at the end of class, so we should probably just go back through this quick. The final reactions of the alkynes were our reduction reactions. And we know they're reduction reactions because these molecules are gaining hydrogen, right? So then I don't have to mess with the oxidation numbers. But if I'm going to reduce a triple bond, in order to have the greatest toolbox necessary of reactions to make things, I'd like a reagent that'll give me an alkane. I would like a reaction that would give me a cis alkene, and I would like a reaction that would give me a transalkene. Okay. And so if we think about the reagents that we talked about for hydrogenation or reduction of a double bond, we just had one. If I want to take a double bond and I would like to add 2 hydrogens to it in order to reduce that double bond, I used hydrogen and what reagent? It's a metal. Palladium, PD, or platinum, PT. So we used either palladium or platinum as our metal. And so we added the hydrogens 100% cis, as I've drawn here. So the issue is, okay, how do I do each one of these, in essence, hydrogenations? And then why do we get the product I get? Well, let's kind of think this through. Maybe we can memorize this, or we can just kind of think through. So one of the issues is that if I use hydrogen and palladium or platinum, I'm going to get the alkane. And you might say, why? Well, what happens when the triple bond gets reduced by 2 H's? It goes down to the alkene. But if there's extra hydrogen there, then that's going to react with the double bond with palladium or platinum and go all the way down to the alkane. If I was able to measure 1 molar equivalent of hydrogen, I would get a mixture of products. Because what would happen is that some of the triple bond would be reduced to double bond, and then some of that double bond would immediately react with hydrogen that's available. The reality is I can't control the amount of hydrogen that's there, so I've got to do an excess. And so when there's excess hydrogen there, I'm just going to take the triple bond all the way down to the single bond. Because the palladium and platinum is active enough to reduce a double bond. Okay. So if I just use the hot catalyst like palladium or platinum, I don't have a choice. It's going all the way to the alkane. So then somebody said, well, I'd like to stop at the alkene if I could, please. And so the thought process there is, I need a catalyst that's less reactive. Because a less reactive catalyst that won't add hydrogens to a double bond will stop. And so the terminology that we use for basically killing the activity of a catalyst, or at least wounding it severely, is poisoning it. So Lindlar was, I believe, the first one to say, if I take my palladium metal and I add something like, I think it was either barium oxide or barium carbonate to it. We'll just say it was barium oxide. And then he had this, it wasn't a naphthalene, it was a quinone. Or it was something that looked like that. When they react, when you add these things to the palladium metal, the barium oxide and the organic molecule here, it basically reduces the activity of the platinum. It basically poisons the surface. So that now this Lindlar catalyst cannot react with the double bond and hydrogen. It's not active enough. So this is what's called the poisoned catalyst. And this was intentionally done so that you would stop at the cis alkene. It's still cis because the hydrogen absorbs onto the surface of the metal, and then both those hydrogens add to the double bond at the same time. So it's still a metal surface reaction. It's just it's not active enough to reduce the alkene. So that's what the Lindlar catalyst is. And you don't have to know what these things are. You can just say Lindlar. And if on like the final exam they put this stuff, then I go in there and I write Lindlar. So the Lindlar catalyst lets you stop at the double bond and add cis. Whenever you use like palladium or platinum metal, you use catalysts. Usually we're on the guard to not get the catalyst poisoned. Like in the refining process, if you go to a refinery, then they're taking crude oil, which is long chains of carbon, and their catalysts are chopping them up to smaller chains, like 8 chains for octane, that we can use as either gasoline or fuel oil, but they're chopping the long chains up. And there they have a problem because the catalyst, if there's sulfur in the crude oil, the sulfur will kill the catalyst or poison it. So normally we don't poison catalysts intentionally. We have to be careful that they don't become poisoned during a process, because palladium and platinum is super expensive. And so having those catalysts get basically destroyed without a method of regenerating them is going to cost a fortune. So there's a lot of these kinds of those are called cracking reactions, and they're done by catalysts, and people spend a lot of time trying to understand exactly how the catalyst gets poisoned, and also how the atoms break apart, or how the hydrogen maybe adds. And it's not, the surface of these reactions isn't well understood. It's not well understood. Good enough for us to have refineries that can take long chains down to small ones. If we could do the other, if we could take small methane molecules of natural gas and make gasoline out of them, that would be, we could take all of our natural gas and make gasoline out of it, but that's still a work in progress. So then somebody said, but I want trans. I want the trans alkene. So then we have to go to a completely different mechanism. Then what we're going to do is we're going to use sodium metal in liquefied ammonia. So first thing is, this is, I think I might have said this on Wednesday, this is not NaNH2, because NaNH2 is NH2 minus. Now, we usually don't write the counter ions because then the counter ions end up everywhere. Like, they'll end up in the middle of a cyclohexane ring. I have no idea how they got there, but they will end up there. And then I gotta use a lot of red pens. So sodium's just a counterion in that case, but this is not sodium metal and liquefied ammonia. So then the question is, liquefied ammonia, how do you do that? Pretty easy, because ammonia basically liquefies at about minus 20 degrees, minus 30, minus 20, minus 30. So what you do is you take a round bottom and you put it inside of a dish that's cooled with dry ice, solid carbon dioxide, and usually like rubbing alcohol, isopropyl alcohol. That bath is about minus 78 degrees Celsius. And then we need a sort of a condenser, but not a standard condenser. We need a condenser that kind of comes up like this. There's an in and an out, but then the actual condenser part is like a test tube where you put your dry ice isopropanol, and then when your ammonia comes in, it liquefies, drips down into the round bottom, and then eventually you can have like half a round bottom filled with liquid ammonia. Now you got to be careful with this because number one, it's ammonia, and we all know what ammonia does when it gets inside of your lungs, and before that when it gets into your nose, right? That's smelling salts. And the other thing is, if you have a lot of liquid here, a lot of liquefied gas, if it gets warm too quickly, it generates a lot of pressure and then just blows this whole thing up. And then you have a room full of ammonia gas, which is going to be tough on everybody's lungs. But you can make ammonia. You can make liquefied ammonia. Then what you do is you put a drop of sodium metal in it. Now, sodium metal has an unpaired electron that it would love to get rid of. So what happens is when the sodium goes into the liquid ammonia, it becomes a sodium plus, and then the electron just kind of like goes around the solution. It becomes what's called solvated. It's a free electron. Now that's the most powerful reducing reagent you can have, right? If gain electrons is reduction, the best way to reduce something is to just have a naked electron running around to add to it. I mean, you can talk about batteries and everything else, maybe a current, but this predates batteries. So this is how you can make a solvated electron. The solvated electron is dark, makes the solution dark blue, and so it's a fairly spectacular reaction as long as you don't blow it up. And so what happens in this case is, with the triple bond, and there's a mechanism written out on this from, I think, Wednesday's video, but what happens is when we take our alkene and we have our solvated electron running around, what happens is the solvated electron adds to one of the two carbons. And notice I used a half arrow there, a fishhook, because that's one electron. Now, if it adds to that carbon and nothing happens, I still violate the octet rule. So what's going to happen is this pair of electrons is going to go to the carbon as a pair. So what I'm going to end up forming then is a carbon with a lone pair and a carbon with an unpaired electron. And now I have to put those in orbitals. And by definition, since they're big clouds of electron density, they have to be trans. So when the unpaired electron cloud and the pair of electron cloud gets set up, it has to be trans, because otherwise we'd have two big negative charges next to each other, which is unstable. So this carbon has a negative charge. This carbon over here is 0 because it's just a radical. So this is actually a radical anion. That's different than yesterday's, or not, well, yesterday for me than some of you. But for mass spec, we make radical cations. This is a radical anion. But this is what sets the trans geometry. Then this is nothing more than a C minus. The C minus is going to grab, bless you, is going to grab a hydrogen from the ammonia. So that carbon's going to then get a hydrogen there. And then the carbon with one electron, now a second solvated electron comes in, adds to that carbon. It now becomes negatively charged. And so then it then is a C minus, removes the hydrogen from the ammonia. Not a mechanism I would ask you to reproduce, but the reason I showed it in the video and I'm showing it again here is because it's that radical anion that sets the geometry for it to be trans. Completely different mechanism. And this is a very old school way of doing a reaction, because I don't know I know the last time I ran a liquid ammonia reaction, and that was like 1990-ish. If you weren't born then, I don't need to know because I already am old. I know that. But that's the last time I ran one. But it's a great a way to reduce things. And it's just a spectacular blue color, as long as you keep the liquid ammonia under control. Josh?
So there's two electrons in total that are transferred, and then there's 2 units of NH3 that are used as well.
Right. So the NH3 is the solvent, and so really you would need 2 equivalents of sodium for every 1 alkene or alkyne. But the idea here is that the mechanism for the poison catalyst is having the hydrogen on the surface, adding it to the same side. Completely different mechanism to get trans. But in the end, I now have 3 things that I can do with the triple bond as far as reductions. I can make the alkane, I can make the cis alkene, and I can make the trans alkene. And so that's useful from the standpoint of making different molecules. So that was kind of last, because we talked about oxidation. If you want to cleave a triple bond, you got to use the strongest reagent, which is KMNO4. And once you cleave that triple bond, there's no question about it's an aldehyde or a carboxylic acid. Carboxylic acid all the way. So the only other thing from questions? The only other thing in the review stuff is the idea of carbocations. So what's the most stable carbocation? Tertiary. Stable carbocation? Why not? That is what's called a primary allylic carbocation. The allylic position is the one that's attached to a double bond. Now that, let's see, we talked about geminal, we talked about vicinal, we talked about vinyl. If that was a chloride, it'd be a vinyl chloride. But when we talk about radicals and carbocations, that becomes an allylic position. So this is a primary allylic carbocation, and it is stable. And why is it stable? What if I do this? What did I just write? It's resonance structure. So this isn't a run-of-the-mill primary carbocation. It's primary allylic, so it's more stable. It actually can form in solution. Now, it'd be better if it was a secondary allylic or a tertiary allylic, but primary allylic is okay. And then I'll just throw this in. Benzylic is like allylic, it's just when the plus charge is next to the benzene ring. And we can draw resonance structures for it as well. We can draw a resonance structure by moving the double bond here outside the ring, and then there's plus charge, then I can actually draw 2 more resonance structures. So allylic and benzylic carbocations are stable. Now, how stable are they compared to like a tertiary? I think, but I don't know. Because, and I'll just show you our latest problem, Brian and I's latest problem, that we've been adding like HCl to this molecule, thinking that it could do one of 2 things. It could either form, the H could add to this carbon and then put the plus charge there, or you could add the H here and put the plus charge there. So we're doing HCl addition to an alkene. Nothing new here except the benzene ring. So in the past, I would have said, we have a secondary benzylic carbocation versus a tertiary carbocation with no possible resonance structures. And so I would say, which one of those 2 is more stable? And I would have probably given preference to the secondary benzylic one. Except that actually when we did this reaction, we get like, one way we do it, we get 100% of the chlorine adding to this position, which means that it's more stable than the benzylic one, which I'm puzzled by. But it happens. So there's probably, I think we suspect a reason, but we're going to have a hard time proving. We're going to have to prove it. But that kind of defeats my purpose of that all those resonance structures make a difference in this case. So I don't know that anybody's come up with a table of ranking all the different carbocations, but I think like an allylic is probably on the order of a tertiary carbocation in terms of stability, and then secondary would probably be more. Just our thought here is well, I'll save it for when we talk about allylic carbocations. The ring has to actually be parallel, has to be like parallel, and it can't be, so as it twists, we don't get full stabilization. Okay. So that's now foreshadowing at least 2 of the labs next week when we talk about fragmentation patterns in mass spectrometry. We're going to talk about these carbocation resonance structures because it's going to reinforce that, and that's what happens in mass spectrometry. So next week, if you have Dr. Simmons and I, that's all I can guarantee, you're going to see more of these types of carbocations, and I'm not sure if you guys did fragmentations in Dr. Kwan's lab, but you may. Okay. All right, so I'll take your homework problems. You can put them on one of those chairs over there. If you had any questions about them, you can hold on and ask me. Otherwise, the only thing on Tuesday, I will release a video for you to watch, but then the review problems will be there. If you have any questions, email me or come see me. Depending on how big the snow is, I may be here or not. Snow doesn't bother me, but 7 to 15 degree wind chills, I'm sure my battery's not going to like that, so I may want to stay in the warm garage. But if you have any questions, shoot me, and I can shoot me an email, and I can send them to you.